Swayam Prabha. Digital India. Educated India.
Now, given rho pi 1 bar, we can now uniquely identify C1. Okay. So, essentially if I am given rho pi 1, note that by our construction, so these remaining things can be anything, but by our construction C1 is once again the first clause that is unrestricted with respect to this restriction rho pi 1. Okay. So, if I am given this restriction, then I can uniquely identify what my clause C1 was. Okay. And we will see later on that, and with some more info we can get pi 1 and pi 1 bar as well. So, what that information is we will see later on, but the key thing is that to find out C1, if we are given rho pi 1 bar, we can uniquely identify C1. Okay. Now, what is the set, I mean what is the size of this restriction, or from which set do we pick this restriction? So, how many variables are being fixed over here? So, rho fixes how many variables? L variables. How many variables pi 1 bar is fixing? D1 variables. Okay. So, the number of variables that are unfixed is L minus D1, right. So, rho pi 1 bar, so note rho pi 1 bar belongs to R L minus D1. So, in rho basically L variables were unfixed, now I have fixed another extra D1 variables. So, rho pi 1 bar belongs to RL minus D1. Okay. So, now we continue in this manner. So, we define C2. Okay. So, C2 is defined to be the clause or the first clause that is unfixed by just read this. Not fixed to 1 by rho pi 1. Okay. Pi 2 is basically the remaining set of variables, that is, it is a restriction of pi minus pi 1, okay, to C2, and let us say that D2 is the size of pi 2. Similarly, pi 2 bar is the unique setting of variables in C2 such that C2 is not identically equal to 1. Okay. So, we just continue in this manner. So, we have row pi 1. Okay. So, in row pi 1 C1 got set to 1. Now, look at the first clause that is not set to 1 by row pi 1. Okay. So, it is only setting some d1 variable. So, there will be some other clause that is not being set to 1. Look at that clause, look at the remaining set of variables in that clause. Okay. So, from pi remove the variables of pi 1, okay, and look at the variables that are present in C2. Okay. So, this will be our C2 in this case, so row pi 1. So, this is our C2. Okay. So, look at the remaining set of variables. Yeah. So, look at the remaining set of variables over here. Okay. Now, pi 2 bar once again is the unique setting of those variables such that C2 is not 1. Okay. And we keep on continuing this. Okay. So, how long do we continue? So, we will continue unless and until we get S variables. Okay. So, in general, let me write this, Ci is equal to first clause, that is not fixed to 1 by row pi 1, pi 2 up to pi I minus 1. Now, pi I will be the restriction of pi minus pi 1, pi 2 up to pi I minus 1. So, remove all these variables from pi and look at what remaining variables belong to this clause. Okay. And now, pi I bar is the unique setting of the variables sorry, this one is not C2, this is pi 2. So, unique setting of the variables in pi 2 such that C2 is not 1. Okay. So, unique setting of the variables in pi I such that Ci is not identically 1. Okay. So, we continue or let me just write this as we end this process once we have restricted exactly S variables. Okay. So, we get pi 1, pi 2 up to pi k, and correspondingly pi 1 bar up to pi k bar. Okay. So, what are we saying? So, well, in first stage we have restricted D1 variables, then we restrict D2 variable. Okay. In the ith stage, well, I have not written it over here, but I can write it over here. Di is basically the size of pi I, right? How did I write this? Yeah, Di is equal to size of pi I. So, we continue till we reach a point where the sum of these Di's is exactly equal to S. Now, note that what do I mean by exactly equal to S? Now, look at this last restriction. So, in that last restriction, it is not necessarily that I will be restricting all the variables. So, basically I would have found a clause Ck which is unrestricted. So, in Ck I will only pick that many variables which would give me a total of S fixed variables. Okay. So, note in the last step only a subset of the variables in of pi might be restricted in Ck, but that is okay for us, it does not matter. Even restricting a subset will keep that as unrestricted. Okay. So, now
So, in this subset in the last clause, will we select the
first, yeah, first few variables such that it becomes exactly S. And now I look.
It won't matter if like none of the like the restriction just restricted to these variables, if it does not set it to 1.
It, well, with setting so restricting it to those variables will not set f
F row
pi 2 up to pi k to 1, it will not set that clause to 1. Okay. But that actually does not matter to us. What matters to us is that even f restricted to row pi 1 bar, pi 2 bar up to pi k bar will not set that clause to 1. That will be true, and that is actually what matters for us. Okay. That is what we will be using next. Yeah, actually I think I can erase the statement of the lemma as well, because we are just proving a slightly different thing. Okay. So, let pi star bar be equal to pi 1 bar, pi 2 bar up to pi k bar, and rho star is equal to rho pi star bar. Okay. We will also define two strings. So, remember that what I said is that firstly we will be identifying these clauses. So, we saw how we can identify C1. Okay. Now, note that if we are given row pi 1 bar, pi 2 bar, okay, then and along with it I am also given, let us say, what pi 1 bar is. Okay, so, I fix according to, or sorry, let us say I am given pi 1 and I am given row pi 1 followed by pi 2 bar, then I can uniquely identify C2, right, because C2 will be the first clause which is not set to 1 by row pi 1 pi 2 bar, because pi 1 is already setting C1 to 1, and by our construction, that is the first thing. So, that will give us. Now, the question is that we can identify these clauses in this manner, but how do I get pi 1 pi 2 bar? Okay, so, I said that with some little bit of more information I can actually get what these restrictions are as well. That is what I will define next. Okay. So, define for all I belonging to 1 to k, okay, ai belonging to 0 1 to the power t. Okay. What was t? So, t was the, so we took a TCNF. Okay. So, t was the maximum size of a clause. Okay. So, essentially what I will do is, so a I of j, so the jth bit, so ai is basically a t bit string. So, the jth bit of ai will be equal to 1 if the jth variable in C I is set by pi I and it is equal to 0 otherwise. So, if the jth variable is one of those di variables. Okay. So, note that in Ci there are di variables which are fixed by pi I, right. So, if the jth variable is one of those, so that fixing can either be fixing to 0 or fixing to 1, then I will set ai j to 1, otherwise I set it to 0. So, essentially what ai helps us in figuring out is which are the variables in a clause that are being set by pi I, okay, and I have k of them. So, I know all, I mean I know it for all pi 1 up to pi k. I will also define another string define b belonging to 0 1 to the power s as, so b of I is equal to the have I written it? Okay, equal to the value to which the ith variable is set to by pi 1 up to pi k. Okay. Yeah. So, note that we are fixing a total of s variables. Okay. So, we had chosen pi 1 up to pi k such that s, a total of s many variables were getting fixed. So, bi is basically the value to which these restrictions are fixing those s variables. Okay. So, the exact value. So, if let us say pi and of course, note that all these pi's are distinct by the construction, they do not overlap, all of them are distinct. So, if some pi t some pi k is setting, or pi not k, pi maybe pi g or something, if pi g is setting some variable to 0, then b of I of that variable bi will be 0 and otherwise it is 1. Okay. So, now the last, or not the last, but the second last claim is why is this an injunction. Okay. And lastly, we will talk about the size. So, claim given rho star these ai's I going from 1 to k and b, we can uniquely construct row. So, if I am given this row star, that is row pi bar or pi star bar, and these strings ai's and b, then I can uniquely construct my function row, and not just row, we will show that we can actually get all of these pi i's and pi I bars as well from this. So, this proof is actually easy, it follows by our construction. So, once again, first we will get C1. What is C1? Okay. So, C1 is the first clause not identically 1 with respect to row star or let me use the notation actually instead of writing this manner. The first clause in f restricted to row star, that is not identically 1 is C1. So, we get what our C1 is. Now, we use A1 and B to identify pi 1 and pi 1 bar. How do we get it? So, I have C1, I look at A1 first. So, A1 will tell me exactly which are the variables which were set by pi 1, I know what those variables are. B will tell me what are those values that they were set to. Okay. So, it now tells me what pi 1 is. Now, once I know pi 1, I have my clause C1, I can look at the clause and I can look at my values of pi 1 and I can get pi 1 bar, because pi 1 bar is a unique setting of those variables such that that clause does not become 1. Okay. So, I have this. So, I have gotten pi 1, I have gotten pi 1 bar and I have gotten C1. Now, next I again go in a iterative manner. So, let row 1 be equal to row star minus. So, in row star what do I have? In row star I have row followed by pi 1 bar, pi 2 bar up to pi k bar. So, I will remove pi 1 bar from row star. Okay. Now, those variables which were being restricted by whatever pi 1 or pi, in this case pi 1 bar, I remove them from row star. Okay. And I will add the restriction pi 1. Now, what does this achieve? This is exactly what I said earlier. What this achieves is that this makes C1 equal to 1, because pi 1 makes C1 equal to 1. So, now what can I say about row 1? What can I say about this? Exactly. The first clause here that is not identically 1 is C2 now by the very construction. Okay. Okay. So, first clause here not identically 1 is C2. Okay. Once again use A2 and B to get pi 2 and pi 2 bar. Now, continuing in this manner, we get pi 1 up to pi k and pi 1 bar up to pi k bar. Okay. So, now here you can see why we only getting a subset of the variables of the last clause was good enough for us, because what we only want is that that clause should remain unrestricted. That is the only property that we are using here. It is not necessary that each of those variables are being set to 1 by pi k, that is all, okay, because after that we do not proceed anymore. So, this proves that it is a injective function. So, given rho star a I b, I can uniquely okay. So, I have gotten this. So, now I have all this. So, how do I get rho? So, what is rho? So, I know all of this, I know rho star. So, therefore, we can obtain rho. Okay. Just remove these restrictions pi 1 bar up to pi k bar from rho star, that is all. So, this completes the proof of this claim. Okay. So, now we have established that it is a one-to-one function. What is left to prove? That the size of this string, or this string actually comes from a set of size whatever r, whatever was it, r l to the r to the power l minus s times w. So, that r to the power l minus s is clear, because so how many variables are restricted in rho star? So, already I have L variables restricted by rho, and pi star bar is restricting another S variables. Okay. So, rho star belongs to r to the power L minus S. Okay. So, that many variables remain free. So, that part is done. So, now we have to show that and what is the size of the string B? So, B B belongs to 0 1 to the power S. So, B comes from a set of size 2 to the power S. So, we have R L minus S, we have 2 to the power S. So, now the only thing that is left to show is that I going from 1 to k comes from a set of size how much? How much do we need? So, W was 4t to the power s, I already have a 2 power s. So, what remains is 2t to the power s. Okay. So, this I will so there is just 2 observations which will actually give this. The first observation, what is the structure of these AIs? Okay. So, note that each AI comes, so each AI is basically a binary string of length t, and each AI has at least one 1, right, because at least one variable. So, in each of these pi i's at least one variable gets restricted, okay, and the total number of ones in all the AIs is how many? S. The total number of variables that are getting restricted is S. Okay. So, each AI has at least one 1 and total number of ones in all the AIs is equal to S. Now, using these two you can find out that the, so I will just leave this as an exercise, that the number of sequences of the above form is at most 2t to the power s. Okay. Also note one more thing, that k is actually less than or equal to s. Okay. So, the number of pi 1 up to pi k, that is at most s, because in each of these there is at least a single one. Okay. So, you can, so this is again a simple combinatorial argument, you can think about this. Okay. So, this completes the proof of Hastad switching lemma. Okay. So, the key aspect, I mean, of course, this is a very complex proof, and okay. So, one more thing that I should mention here is that the proof that Hastad actually gave, so this proof was given by Hastad during his PhD. Okay. So, this was part of his PhD thesis, and the proof that he gave was slightly different. He gave a probabilistic argument. He did not explicitly give the construction of all this. So, he argued that such an injection actually exists. So, this constructive proof was actually given later by Razborov. Okay. So, Razborov, so this proof is actually even simpler. So, his proof, Hastad's proof is a little bit more complex, but this was a simpler proof that was given by Razborov. And what else did I want to mention? Yeah. So, of course, we in this lecture we only proved it for the constant 16, but as I said that with a little bit more work you can actually prove it for gamma, where gamma equals 4.16. And also the other thing is also true, even if you prove it for 16, you can also prove the size lower bound with the constant 16 as well. Okay. You can actually modify the proof that was given last time so that it works with the constant 16 as well. So, both ways are actually open. Okay. Okay. So, I will stop here. Yeah, yeah. So, that, as I said, it actually comes from solving an equation. So, you get a equation using this, I mean, so basically they showed that this is bounded by some alpha to the power s, and that alpha is basically an equation which has this TP TPNN, and then they showed that solving that equation you get it as gamma, you get alpha as equal to gamma PT. So, gamma PT is one of the roots of that equation. It is a, yeah, so it is a, I mean it is not a linear equation, I do not remember. It's an exponential equation, yeah, yeah. See, there are actually many places where we can improvise a little bit, right, because if you remember last time the probability p that we took was how much? It was n to the power minus 1 over d minus 1, right, and we just said that, well, that is less than half for d greater than or equal to 3, but if n increases, actually that becomes much lesser than half, and here we are only showing it for n for p less than half. That is one place where you can improvise for large n of n, right. And the way, yeah, what else? Yeah, I think the way we did that counting, I think I have erased it, but so where we had this 2 factorials, okay, and we took that ratio of 1 factorial over another, and we took the maximum term of the top factorial over the minimum term raised to the power s. I think that can also be improvised. So yeah, yeah. So I do not know much how that thing works, but of course it can be made smaller. But the important thing is that the essential idea is this construction of this injection. Okay, so construction of this one-to-one map, and yeah, so this is the crux of the proof. It is, yeah, it's a general function. It is a general function. No, it's not, well, it is not a general function actually. It is a function which is representable as a TCNF. Now, any function, as I said yesterday, that day before yesterday, that any function can be represented in CNF form or DNF form, right. But for small t's, it is not necessary that every function will be representable. If you take t to be large enough, of course, if I take t to be n, then any function is representable as NCNF or a NDNF, right. So, yeah.